Chapter 13 is going to deal with gas laws. I just want to give a qualifier to this PowerPoint. It's totally stolen. I don't know who made it, but I appreciate it, and made a few changes, but I'm going to use it for this chapter. So we're going to talk about gas laws. We're going to start with the physical properties of gases. The kinetic molecular theory is going to be what we're going to talk about first. Particles in an ideal gas are different than particles in a real gas. So in order to use or apply the gas laws, we're looking at them being under ideal gas conditions. So particles in an ideal gas have no volume. They have elastic collisions, which means that they bounce right back. They're in constant motion. They're straight and random line motion. They don't attract or repel each other, and their average kinetic energy is directly related to the temperature that they're at. So we increase the temperature, we increase the kinetic energy, and they bounce around even more. So in real gases, things are a little different. In a real gas, remember that gases have their own volume. They attract each other. And gas behavior is most ideal at low pressures and at high temperatures and in nonpolar molecules so that there's not an attraction between them. So again, we're going to look at what gases would be like under ideal conditions. Remember, there's a lot of difference between a solid, a liquid, and a gas. So a gas is going to expand to fill any container that you have it in. They are molecules that are under random motion. They don't really have an attraction for each other. There's so much space in between that they just bounce around. The gases are actually fluid-like, like liquids. Again, there's no attraction. They have very low densities, no volume, lots of empty space. So here's our solid, our liquid, and our gas. You notice the vast amount of difference between the amounts of space between the molecules. Gases can be compressed. There's a lot of empty space to compress. They can undergo diffusion and effusion due to random motion. And this is just pictures that show that. And you notice we have compression of the gas here. We still have the same number of molecules, but just in a smaller volume due to compressing the space that's in between the molecules. In these pictures on the right-hand side, you'll notice that this is diffusion. So we have gas molecules go from an area of greater to an area of lesser concentration through an opening. And this is a diagram of effusion where you see it going through a membrane instead of through one set opening. So let's talk about temperature. We're going to always use absolute temperature, which is Kelvin. And when we use Kelvin, we have to make conversions, of course, because Kelvin is not on the same scale. So you have to remember how to convert. So if you're given Fahrenheit, you're going to use this formula to convert to Celsius, and you can always change Celsius then to Kelvin. So a lot of times the problems we're going to work with, they will give you Celsius and you'll have to change it to Kelvin, but you have to remember to change it. And if it's in Fahrenheit, change to Celsius first. Let's talk about pressure. Pressure is force over area. So area, let's say area is 1, and the force that I put on that area is 6. Well, 6 divided by 1 is a pressure of 6. What if I keep the same force and increase the area? So let's say I keep the force at 6 and the area I'm going to increase to 3. The pressure goes then from 6 down to 2. So if I increase the area and put the same amount of force on it, it's going to decrease the pressure. So if we look at these 3 different pairs of shoes, we have the snowshoes with a big surface area. We have tennis shoes that have a surface area not quite as large as the snowshoes. Then we have high heels that have a smaller surface area. So if I were to put the same amount of force on all 3 of these types of shoes, which ones are going to create the most pressure? Well, it would be the ones with the least amount of area. So in this case, the high-heeled shoes would put the most pressure with the same amount of force on whatever it's putting its pressure on. We measure air pressure by using a barometer, and this is a mercury barometer. And the height of the mercury in the tube is going to depend on how much pressure is being put onto this bowl of mercury by the atmosphere. So as the atmospheric pressure increases, so will the amount of mercury in the tube. It will increase as well. So this is measured in millimeters of mercury because it is a mercury barometer. On the other hand, we can use a manometer to measure the pressure inside of a contained gas. And the way that we do that is we look at the pressure differences in the 2 different arms of the U-tube. And this is a U-tube, not a YO tube, so you can't find a channel. But it's a measure of the pressure of the gas sample. And the units for a manometer, there are various units that you can use depending on how it's being measured. So let's take a look at the type of units we're going to use to measure pressure when we do gas laws. So let's take a look at these. These are equivalent to each other. So I can say 101.325 kilopascals or kPas is the same thing as 760 millimeters of mercury. I can say 1 atmosphere is the same thing as 14.7 psi, which is pounds per square inch, which is an English unit that we use when we measure the pressure of the air in our tires. So all of these are equivalent to each other. A pascal, just for reference, is a newton divided by a meter squared. So it's the pressure that's put with the unit of force called the newton, and the area is over a meter squared. One thing to keep in mind is that a pascal and a kilopascal, of course, are related. That if I take 1,000 pascals, I have a kilopascal instead. So if I wanted to look at a pascal unit, 1 pascal at sea level would be 101,325 pascals, which is 101.325 kilopascals. So that may come up when you're doing your conversions as well. STP is standard temperature and pressure. So standard temperature and pressure is at 0 degrees Celsius and 1 atmosphere, or 273 Kelvin and 101.325 kPas. So at these conditions, under these conditions. It's important for you to memorize this because we'll get into some problems where they'll say this is the information about this gas, these are the conditions it's under. What would this be if it changed to STP? So you are expected to know that, oh, well, STP is 0 degrees Celsius and 1 atmosphere, or 273 Kelvin and 101.325 kPa. So you need to memorize those. We're going to do a few problems. These are super simple problems just to get you back into the habit of doing conversion factors. So we'll go through them real quick. The average pressure in Denver, Colorado is 0.830 atmospheres, and it wants us to express this in millimeters of mercury and in kilopascals. So you're going to set that up with a conversion factor. The conversion factor that you're going to have is going to come off of the slide that has the various pressures at sea level. So we're going to take this one, for example, and use 1 atm as 760 millimeters of mercury, being the same thing. We're going to be able to cancel when we set it up that way. We do the simple math. So the 0.830 multiplied by 760 divided by 1 is 361 millimeters of mercury. Part B says to take it to kPas. So we're going to take the 0.830 atmospheres and use this conversion factor this time with 1 atmosphere equaling 101.325 kPa. Do the math, and we end up with 84.1 kPa. Second gas pressure problem. Convert a pressure of 1.75 atmospheres to kPa and millimeters of mercury. So we have 1.75 atmospheres. Conversion factor again, 101.325 kPa over 1 atmosphere to be able to cancel our units and get 177 kPa. 1.75, we're going to take it to millimeters of mercury. Again, 760 over 1. Get rid of your units and end up with 1,330 millimeters of mercury. Convert a pressure of 570 torr to atmospheres and kilopascals. Remember the decimal point right here makes these three numbers significant. So just to brush up on your sig figs. So we have 570 torr, and we're going to change it to atmospheres. Simple as that. The next one is 570 torr, and we're going to change it to kilopascals, and there's our relationship between kilopascals and torr. All we have to do is cancel the units and get our answer. So the math in this chapter is not very difficult. However, you all have upper level math classes, so the chances that you're going to make silly mistakes increases because you're going to think you can just buzz through all this. One of the things I want to make sure that you remember to do is to set up your problem and show where you cancel your units. No work, no credit, so let's practice.